very important here. So we're going to look at section 3.3 today. I am skipping over section 3.2 on purpose. We will come back and get it later. Today we're going to look at 3.3, which is on when functions are increasing and decreasing. So we're going to look at where functions are increasing and decreasing, and we're going to look at something called the first derivative test. I'm going to do one example of each, and that's that. Okay, this is going to take a little bit. Hopefully you watched my video that I posted. Hopefully you watched it before now, but if not, you're going to see it basically the same stuff here. We're going to skip the warm-up because we already did a different warm-up. So here's the first thing. First idea for the day. How do we determine where a function is increasing or decreasing? Well, here's our theorem. The test for increasing and decreasing functions. Let f be a function that's continuous on a closed interval and differentiable on the open interval. Well, here, let me just kind of summarize it for you guys. Let's say you have a curve like this. What is a derivative? It is the slope of a tangent line, correct? Slope of a tangent line. So if I drew a tangent line right here, which I didn't do a very good job of, but let's pretend that's a tangent line. What would the slope of that tangent line be? It'd be positive, wouldn't it? It's the derivative, but it'd be positive there, wouldn't it? Similarly, what if I drew a tangent line over here? What would the slope of that tangent line be? That'd be positive. And that's what this theorem, and by the way, guess what's going on with the function here? It's increasing, isn't it? Guess what's going on with the function over here? It's increasing. It's kind of intuitive, really, when you think about it. And here's what it says. If f prime is greater than 0 for all of the x's in the interval, then the function is increasing on the closed interval. That's it. And it makes sense. If all the derivatives are positive, then the function is going up. It's getting bigger. It's increasing. That makes sense. The rate of change is positive, which means it's adding. It's increasing. Similarly, what if I drew a tangent line somewhere, let's say here? Let's see right there. That's a horrible tangent line. There's your tangent line. What's the slope of that tangent line going to be? It's going to be negative. That's a negative slope, isn't it? And if f prime, the slope of the tangent line, is negative in the open interval for all the x's, then we're going to say that f is decreasing on the closed interval. So let me summarize this. The first derivative of the function tells you where the function is increasing or decreasing. Let me say that again. The first derivative of a function tells you where the function is increasing or decreasing. Now there's one more scenario, and I didn't really draw it in this picture, but let's say you had a graph that did this. Let me do this in a different color. Let's do black. Let's say we had a curve that did this. It goes up like this, and then it goes straight across like this, and then let's say it goes up some more, something kind of ridiculous like this. Perfectly horizontal right there. What would the slope of the tangent line be here in this region? What would the slope be? It'd be 0, right? Because it'd be a horizontal tangent line, correct? Guess what we call those kinds of functions in that area? And that makes sense, doesn't it? Increasing means as you move from the left to the right, the function's going up. Decreasing means as you move from left to right, the function's going down. Constant means the function's not changing at all. It's staying the same. F of 5 is, let's say, 7. F of 6 is, let's say, 7. F of 7 is, let's say, 7. The function's staying 7. It's constant. So if f prime is 0, in other words, the slope's not changing, it's staying the same, it's constant. Let me say that again. If f prime is 0, the function is constant and is not changing. I think I said that slightly incorrectly. Okay, so let's see an example of that. Now, have you guys ever graphed this function before today? Probably not, right? Let's go ahead and see if we can figure out where it's increasing and decreasing. That's what the question says. Determine where f is increasing / decreasing. Okay, so here we go. Guess what the first thing is we're going to do? We're going to find the first derivative, because that's what we need to do according to that theorem on the last slide. First derivative here is going to be a piece of cake because this is just power rule. I think we get 12x to the third minus 12x squared minus 12x plus 12. Now, would you guys agree that there's a 12 in all of those?
Yeah.
So I could even factor out a 12. I could say that this is 12, and then that'd be x to the third minus x squared minus x plus 1. Something like that. Oh, can I factor that inside stuff? Can I factor these two terms and these two terms? Well, it turns out the answer is yes. So f prime here, we can think of this as 12. Those first two terms have an x squared in common, don't they? Those second two terms have a factor of x in common. Just trust me that I'm doing this algebra stuff correctly. I am. And so we can now finish this off and say that this is equal to 12 times x squared. Actually, I'm not quite done yet, am I? Because guess what can happen with this? What's x squared minus 1 factor 2? X plus 1, x minus 1. So, oh my goodness, this is ridiculous, but I did this one on purpose. You're going to get 12 times the quantity x minus 1 squared times the quantity x plus 1. Now, if you don't quite follow me on this, I apologize, but I just want to make sure. Sometimes I get students who'll say, Mr. Young, you always do the easy examples in class. Well, I personally think that this is an easy example, but there is some algebra there to get this cleaned up. And we want to set this, yeah, sorry.
Sorry, for 12x squared times the x minus 1, isn't it x to the third?
No.
No?
No, so this right here is going to be x plus 1, x minus 1, right? This part right here.
Oh, yeah.
Right? So then there'd be two factors of x minus 1 and 1.
Okay, yeah.
Okay, so now what we want to do is we want to set this guy equal to 0. Now you might say, Mr. Rum, why don't we want to set it to D and E? Well, because it can't be D and E. Is there any way the denominator could be 0? Well, there is no denominator. So it can't be a 0 on the denominator, right? So I'm only interested in when this is 0. So when is f prime equal to 0? Well, it's nice because I spent a lot of time factoring this. What's going to make this term 0? Positive 1. What's going to make this term 0? So that tells us that the critical numbers here are x equals plus or minus 1. Those are the only two critical numbers for this problem. So I'm kind of doing the same thing we did in section 3.1. Now I'm going to do something a little bit different. So I'm going to draw a line right here, and I'm going to call this f prime. And I'm going to make 2 points here. I'm going to make -1 and 1. Can you guys guess why I put -1 and 1 on there? Because they were the critical numbers. They're critical. And now what I'm going to do is I'm actually going to pick values that are not -1 and 1. I already know what f prime is there. What is f prime of -1? It's 0. We just established that. I'm not interested in that, right? What I am interested in is what's going on in between. So let's start in the middle. -1 and 1. What would be a nice, easy number to pick there? Would you guys agree 0? So if I pick 0, so let's say that x is 0. If x is 0 and I plug that into this, then f prime of 0, what would an f prime of 0 be? If I put 0 into this, what would I get? I get 12, which is greater than 0, correct? Which makes it? It makes it positive? Correct. So this is positive. I'm going to put a little positive right there. So we just found that f prime is greater than 0, it's positive. That means that this curve is going to be doing this. And I'm talking now about f. Let me say what I just said again. F prime of 0 was 12, which is greater than 0, agreed? That tells us that the derivative is positive, which means the function has to be increasing. In fact, furthermore, if we go back to what this theorem says, if f prime of x is greater than 0 for all the x's in that interval, and by the way, I don't need to worry about any other x's, right? Because there's only two critical numbers. Then the function's increasing on that closed interval. Let's pick a negative number less than -1. Can someone give me a number less than -1? Make it interesting. -2. That is so interesting. So let's try that one. F prime of -2. Now let's plug, if you guys don't mind, I'm going to plug -2 into this one, okay? So you're going to get 12. And when I plug -2 in there, what are you going to get? -3 squared, right? So I'm going to write -3 squared. And when I plug -2 in there, what do I get? -1, right? Okay. Now, I claim I don't care what this answer is. I just want to know if it's positive or negative. It's got to be negative. Do you understand why it's negative? 12's positive. -3 squared is positive. Times another negative makes it negative. So this is less than 0. Therefore, guess what I'm going to do over here? I'm going to put a minus. And now this is going down. Now, by the way, this F, the red stuff, this is telling us about f of x. The black stuff, in fact, maybe I should make this black here. Maybe make that negative and make that positive. The stuff in black is about the derivative. But the stuff in black is telling us what's going on with the function. Since f prime was less than 0 there, the function has to be decreasing. Would you do me a favor? I've done 2 of the 3. Would you go ahead and try to figure out what's going on when x is greater than 1? I'll let you figure that out right now. Try to figure out what's going on when x is greater than 1. So when I plugged in 1 million to f prime, I get positive. So this is positive here, which tells us that the f function is continuing to increase there. So now we can go ahead and answer our question. In fact, let me go back here real quickly and go back to the theorem. The theorem says if f prime is greater than 0, it's increasing. If f prime is less than 0, it's decreasing. So in this particular case, we have decreasing, increasing, increasing. So I'm going to say that f of x is decreasing. Oops, decreasing like that. Decreasing from, where does it start? Well, -infinity up to what? I think -1, and I'm going to make that closed bracket. Now I'm going to make a note here. I did not close the -infinity because you can't go to -infinity, right?
Because it's an idea.
It's an idea, that's right. But in the description on the theorem on the last slide, we do close this one. And it's going to be increasing. Let's see here. It's going to be from -1 to 1, union 1 to infinity. Oh, I just did what I said I shouldn't do.
Wait, isn't 1 equal 0?
Okay. Oh, and I'll mention something else here in just a second. Yes, Evan.
If 1 equals 0, why wouldn't it have to decrease back down to 0?
So again, if we go back to the theorem says that if the function is, what are we doing, increasing on this part? Yeah, increasing. If f prime is greater than 0, which it is, on the open interval, then we can conclude that it's increasing on the closed interval. So this will work. Actually, let me throw one more thing out at you guys and just get your thoughts. I don't know if you guys are going to appreciate this or not. I'm going to put a slash here. Would it be okay? I'll put a question mark to put -1 to infinity here instead of writing those 2 statements there. Would that be okay?
No. 1 equals 0.
1 is, the derivative at 1 is 0. That's correct. But would you agree that everything to the left of 1, or -1 to 1, everything is increasing? Everything to the right of 1 is increasing, correct? So actually, either of these would be acceptable. Either way would be fine. In fact, so what I'm trying to tell you is if you're like, Mr. Ron, I don't know if this is a better way to say it or this is a better way, just write it one of the other ways and it's fine. Yes?
How could 1 equal 0 and not ever decreasing back down?
How could 1 equal 0? How can the derivative at 1 equal 0?
Yeah, so like the derivative of 1 equals 0.
Good. So do you mind, can we look at this graph? I'm going to pause the video. Let's look at this. Do you guys, does that kind of make sense?
Yeah.
Okay. And again, I tried to pick a problem that was a little bit more interesting. I don't know if I'm crazy here or what, but there we go. But there's the answer. Any questions on this? Yes.
Okay, so I've done the whole WebAssign, and we did the WebAssign, like, every time you turn, you wouldn't put it in the brackets, you put it in parentheses.
Right, because that's the point where it turns.
So then why are we doing it like differently here?
It doesn't matter.
It doesn't matter.
In our book, so here, okay, so I'm going to pause again. Actually, maybe I'll record this. I'm telling you on the AP exam, I didn't want to get in this today because that's not what our book does. But if on the AP exam, if you made this a parenthesis, this a parenthesis, this a parenthesis, and this a parenthesis, you'd still get full credit.
So it's the same thing.
It is not the same thing. So here's the thing. Let's say you went to some other school and they used a slightly different textbook. Their textbook might tell you to do open parentheses. So it's fine.
Okay.
And if you said it's on the WebAssign, then that's fine. Does the WebAssign ask you? Yeah, that's fine. That's good. That's a good question. Okay, moving on. Okay, this is probably the most important test of the entire year. So if there's anything that I think you really need to know in this chapter, it's probably this right here. This is called the first derivative test. And if I were you, I would commit this to memory as much as possible. And my smartboard is acting really weird. I'm hitting the forward.
You're not supposed to talk.
There we go. So they said that the power, there we go. I'll just use my finger. How about that? They said the power went out this weekend, and I don't know if that has anything to do with it. Okay. So the first derivative test says, let C be a critical number of our function, and it's continuous. And we also need to know that the function is differentiable except possibly at C itself. So what do we conclude? It's one of three things. If f prime changes sign from negative to positive, it's going to be what we call a relative min. If f prime changes signs from negative to positive, it's going to be a relative min. If f prime changes signs from positive to negative, it's going to be a relative max. If it doesn't change signs, and when I say it, f prime, then it's neither. And I know this sounds like I know it looks like a lot of words, and it doesn't sound that complicated, but every year I teach this class, I'm surprised at how many students confuse this with other things. This is the first derivative test, and we use it to find relative extrema. This is the first derivative test, and we use it to find relative extrema. Next week, we're going to use a different test called the second derivative test, and it is also used to find relative extrema. We do not use this test to figure out where a function is increasing or decreasing. That's what the last theorem was. And I'd like to point out, you guys realize that all of this stuff that's written right here is on the PowerPoint that I post every week on campus, right? Just letting you know that. So I'm glad you guys are writing stuff down. That's awesome. But please don't worry if you don't get it all written down because it's on the PowerPoint. Okay? So I'm going to do one example. And I've picked an interesting one. It's a little bit more complicated than the one on my video. It's going to take me some time, so let's go ahead and get started. How much time do we have? Okay. We get out at 40 what? Sorry, I just want to make sure we don't run over because I'm bad at that. 46, right? Okay, so I got about 10 minutes. Make me be done in 10 minutes. Mr. Allen, how are we supposed to do that? So here we go. Guess the first thing we're going to do is you're going to find the derivative. Everything in this chapter, the first thing you're going to do pretty much find the derivative. Do you guys mind? There's two ways I could go about this. I could do the product rule, or I could do a little bit of algebra so I don't have to use the product rule. What would you prefer?
This is calculus.
Yeah, let's do product rule.
Do the product rule? Okay, so here we go. Product rule it is. So remember, product rule, you got to do 1d2 plus 2d1, right? Okay, this is 1, this is 2. Agreed?
Yeah.
Okay, so g prime is 1, which is 2 minus x, and then I got to do the derivative of 2, which is going to be 2/3 x to the negative 1/3. Plus, now I got to do 2d1. Well, 2 is x to the 2/3. And then the derivative of 1 is, well, the derivative of 2 is 0, and the derivative of negative x is negative 1. Now, guys, I'm telling you, that is the derivative. But I'm going to clean it up a little bit because I've got to set this thing equal to 0 or d and e. Okay, so this is the same thing as 2 minus x, and then we're going to have a 2/3 here in the front, right? So I'll write it like this. And then this x has to come down to the bottom. So let me explain what I did here. There's a parenthesis here too. So this 2, I got to take this 2 times that 2 minus x, right? This 3 is in the denominator, so it's right there. This is a negative exponent, so it has to go to the denominator. Remember, the third power means the cubic root. This guy here is just minus x to the 2/3, no big deal. All right, let's clean this up a little bit. Oh, can I get a common denominator? What would be the common denominator? Well, it'd be whatever this is, right? So it's got to be 3 cubic root of x. So what I'm going to do is I'm going to multiply, and by the way, I'm just doing algebra right now, so hopefully this isn't too much for you. I'm going to multiply this by 3/3 root of x over 3/3 root of x. You guys would agree that that's the same thing as 1, right? Fancy form of 1, sometimes I've heard teachers say. But what this is going to do is it's going to give me the same denominator for both of these things. Okay, so g prime of x is now equal to, and I'm going to go ahead and distribute this. That'd be 4 minus 2x. The denominator here is 3/3 root of x. And now I'm going to multiply those two things. Does anybody happen to know? First of all, 3 is just 3, right? So I'll put minus 3 there. So minus 3. What is x to the 2/3 times, and then that'd be x to the 1/3. It'd just be x. Okay, now we got to be careful here. So there's an x like that. So I'm telling you that this times this is just negative 3x. Do we have any common or like terms in the numerator? What's 2x and 3x?
Oh.
Be 5x, wouldn't it? Okay, so this is my derivative, and I spent a lot of time working on this because now what I need to do is I need to set this equal to 0 or d and e. Okay, so let's start with 0. So I'll do it in blue now. When is g prime of x equal to 0? Question mark. Well, g prime is going to be equal to 0 when the numerator is equal to 0, right? So 4 is going to be equal to 5x. So it looks like x is going to be 4/5 if I'm not mistaken. Agreed? That's the only value where the derivative will be equal to 0. Okay, good. So this is a critical number. So I'm going to kind of point this out right here. Here's a critical number. When is g prime of x going to be equal to d and e? Question mark. Well, we let the numerator be 0. That gave us when the whole thing's 0. How do I figure out where it's D and E? Well, that's when the denominator is equal to 0. We talked about this last week. So the denominator is this part. So now I want 3 third roots of x to equal 0. And that's a pretty easy equation. When's the only time that's going to be 0? Well, okay, if you're not sure, we could divide both sides by 3. So that'd be, the third root of x equals 0 again, right? What's the only value you can put in for x to make that 0? It's 0, right? And this is a critical number as well. Now, if you remember last week, I kind of gave you guys a hard time about whether or not it was in the domain, right? I'm telling you that both of these things are in the domain of this function. Can you trust me on that? So they are indeed critical numbers. Okay, so lots of stuff going on here, right? Haven't even got to the answer yet. How are we doing on time? We're doing great on time now. Okay, so now we're going to do that thing I did on the other slide. I'm going to make a vertical line or a horizontal line. I'm going to call this G prime. And guess what two numbers I'm going to put on there? 0 and 4/5. I was just thinking I probably should double check that I got my critical numbers correct. Somewhere over the rainbow. Yes, okay, good. We're good. Okay, can you guys think of a number that is bigger than 4/5? 1. So let's go ahead and do that let's do it in red. What is G prime of 1? If I put 1 into this right here, this right here. If I put 1 into this, the top's going to be negative, agreed? What will the bottom be? And what's a negative divided by a positive? Yep, so I'm going to write this here. I'm going to put negative over positive, which is less than 0. So this is a minus. That means this is going down. Are you with me? I don't care what the number is. I just need to know if it's positive or negative. What's a number bigger than 1? Or a number bigger than 4/5?
1.
Oh, I did that in the wrong spot, didn't I? Sorry, that should be over here, shouldn't it?
Yeah.
Thank you. The last one we did in the middle. What's a number that's between 0 and 4/5? 2/5. Yikes. With someone with a calculator, I want you to go ahead and figure out exactly what G prime of 2/5 is. I'll give you, use your calculator, use this right here, plug in 2/5 and get the answer and let me know, okay? We're going to do the negative side over here next. So let's do G prime of, what's a number that's less than 0?
-1.
Let's do -1. Okay, so someone's doing that, who's doing the 2/5 one?
I think it's me.
Thank you, sir. Okay. -1. We're plugging -1 into this. When I plug a -1 into here, what's the top become? It is positive. What about the bottom if that's a -1? Negative. What is a positive over a negative? So this is less than 0. So that means that this is doing this. Right? G prime was negative, therefore the function's decreasing there. Did you get the 2/5 yet?
Yeah, it's positive over positive.
Okay, so positive over positive, which is greater than 0, so this is positive, means it's going like this. Now we can get to our final conclusion. We have all that we need. We have all that we need. And if you guys don't mind, I'm going to erase this part over here so that I've got a little bit of room to still write on this slide, if that's okay. I'm just going to erase this part right here. Now, I'm not going to write anything just yet. I want you guys to look. What happened to G prime here to here? It went from negative to positive, correct? If F prime changes from negative to positive, it's a relative min. So I'm going to say right here, I'm going to say, therefore, F prime of, and I think we said 0, is going to be a relative min since, oh, it should be G prime, sorry, G prime, since G prime changes from negative to positive. Has to be. I'm gonna let you write that down. While you're writing that down, once I show you this is gonna all make sense. Hey guys, it went from this to this, right? It went from this to this. What's this? It's a relative min. Doesn't that make sense?
Yeah.
That makes sense. It went from going down to going up. So what happened here? It hit the bottom. Didn't that make sense?
Yeah.
Okay, hey, what happened from here to here?
It goes
It went from
to negative.
up to down. So guess what that has to be? Relative max. So G prime for this is going to be a relative max since G prime changes signs from positive to negative. Guys, I'm going to come back to this slide. Oop. I'm just going to leave it there. I wanted to show you one more thing, but I'm not going to be. Actually, I can do it right here. You remember last week I mentioned the term cusp? You guys remember me mentioning the term cusp? Did I mention that to you guys in here? Okay, so I apologize. Guess what we call this point right here? That's a cusp. This is a cusp. This turned out to be the relative min. And by the way, guess what G prime was there? Guess what G prime of 0 was? Oh, did I do this back? Nope, that's right. When 0, right? This is when x is 0. And guess what this is? X is equal to what here? 4/5. Guess what the slope of the tangent line is there? 0. Guess what the slope of the tangent line is here? Doesn't exist. This is what a cusp is. Thought I did an example like that in class last week. Anyways, I would highly encourage you